screen.
Yes, sir.
Okay, so good afternoon, everybody. How many people do we have on call today?
Okay, we
14.
are currently 14. Yes, sir.
Okay, I expect that. I think the class is full today, and it filled up faster than before. You know, when we talk about today, we are going to be talking about seismic interpretation. And so when you talk about seismic interpretation, everybody is eager. Even people don't want to miss the class. People that have been missing class before. Okay, I'm on slide mode now. Okay. So our objective for this program remains the same. Okay, we've taken care of objective 1, 2, and 3. We are on 4. Okay, which is on seismic interpretation. And all we have been doing so far is for me to help you boost your confidence as fresh graduates or while young professionals with respect to seismic, anything that has to do with the seismic method of exploration. So we dealt with the concepts or the fundamentals. We dealt with the acquisition. We've also talked about processing. So now we're going to dive into interpretation. Okay. For today, our outline will be something like this, up to DHI, and we'll continue by next week. So for introduction, we all know what we've done so far. We've gotten our data from acquisition to processing, and then we want to talk about what it means to do seismic interpretation. So what then is interpretation? Okay. When you say you want to interpret seismic data, you're talking about interpreting an already processed seismic data, not just an acquired seismic. You can't just interpret acquired data without being processed, and I explained that a few of that in processing. So when you have processed the data, you want to interpret it. Ideally, what you're doing is that you want to identify the geologic features that are embedded in the data, these geologic features that give rise to the reflections. So when you say interpretation, you can be interpreting a 2D or a 3D data. And when you are doing that, all those reflections that you got from the subsurface that came as your signals to the receiver, not the noise, because the processing has eliminated the noise to an extent and increased the signal to noise ratio of your data. So your data quality is believed to be okay. So you look at the data and you want to analyze and identify some structural and stratigraphic features that are coming from the subsurface, and you do that using some tools, okay? So the idea is that whatever features you have identified and you have interpreted will be used to model the subsurface, to build a model of the subsurface. Model in the sense that you're building a replica of what the subsurface looks like. So for the example on the page, you have a seismic data. Not too clear seismic data. This data is just for example purpose anyway. The data quality is not looking so fabulous. But at the end of the day, somebody has interpreted it to come up with what is on the lower part of the panel. Okay. So somebody has interpreted this data based on the knowledge of the geology of the area or the basin, and he or she has come up with a model where they have decided that in this part of the data, he has color-coded them into different geologic age. Yeah, okay. And then identify the type of structure in terms of faults, configurations within the basin, as can see in the diagram. Okay, as you can see here, let me get a pen. So someone has actually done this and interpreted this data. So from this person's interpretation, you can see he has mapped out faults from a particular time. You can see that in this data from about 1 second to about 2 seconds or more, that is the area you are having faults, okay? So from here, so that's where you're having structural features. Above 1 second, you're not having structural features, you're having stratigraphic features and all that. And so somebody have done this interpretation. So that's what interpretation is actually all about. You look at the seismic data, you use it to build a model of the subsurface. So the result of the seismic interpretation can vary, okay? Depending on who is doing the interpretation. This data now is looking very poor. You can't even make out the faults clearly. But somebody may have succeeded in interpreting it. Just this, for example, purpose anyway. Somebody has succeeded in interpreting it and building his own or her own model because the person may have been more experienced, may have been working in that area for long, so he knows that he has more experience and he can infer or make a good judgment from the data, even though the data quality isn't so fantastic. So data quality plays a role. Your experience and as an interpreter also plays a big role in your interpretation of seismic data. So that is that. So we dive deeper. So for you to do seismic interpretation, one, you have to look out for the features embedded within the data, okay? You analyze the data to identify basic elements and reflection parameters. When you're looking at the data, you're interested in at what time is so and so occurring. So the time plays a role. How continuous are the events? The shape and configuration of the reflections or the events, the amplitude, okay, the frequency, distribution within your data, interval velocity, and all that. So all these things tends to call it in general the seismic fasces. So you look at the seismic data, you want to identify the fasces. If I may ask, what's the fasces? Does anybody know what a fasce is? If you remember from your geology, what's a fasce? It's a rock fasces or fasces. Any idea?
So I don't know if I'm correct, but sir, can you hear me?
Say what did you have in mind before you conclude whether you're correct or not. Tell me.
Like the different lithologies that have similar properties.
Not ideally similar. It says species are characteristics of a rock that makes it distinct from adjacent rocks. Okay? So anything that makes a rock different from its neighbor. So you can have a thick bed of sandstone. Within the sandstone, who is it again? Excuse me, please. Okay, so within a rock unit, you have different changes that makes each part of the rock unit distinct from adjacent part of the same rock unit. So, for instance, you have a sandstone. As you're looking at it, you're seeing that some places are coarse grained, other sides are fine grained. So that's the fascia, grain size distribution. So the changes within the rock that makes it distinct from one part of it distinct from the other part is what is called fascies. Okay, changes within a rock unit. So when it comes to seismic, changes within the seismic data that makes it one part of the data distinct from the other part, that's the seismic fascia. That's what it means. So when you're looking at your seismic data, you're looking at identifying features that are makes a part of this data distinct from the other part. And these distinctions are caused by geology, okay? These distinctions from one part to the other are caused by the geology. If you remember how reflections occur, what are the fundamentals behind it? Acoustic impedance contrast. So these are the things you're looking out for. Reflection continuity. If I go back to the former slide, somebody has interpreted this data to say that in the upper part, the events are more continuous. So there are no structures, there are no faults. In the lower part, from 1 second down, there are faults. meaning events are not continuous. So that is what I'm trying to explain here. Now, one thing I also want you to know that when it comes to these reflection parameters you're paying attention to when you're doing interpretation, the number 1 to 3 are what you physically see with your eyes most times, okay? In terms of frequency and velocity, you can't, by just looking at the data, especially if you're inexperienced, you can't know the frequency or the velocity except you're using a particular module or icon on the software to identify that. But when it comes to continuity of events or reflection, arrival time, shape and configuration, amplitude, whether the amplitude is high or low, you can visually see that, whether you are an expert or not. You can visually see that. So that is basically one thing to point out. Then seismic reflection parameters make up the seismic species, and they are used to make support your decision making, okay? Because these changes in seismic species are linked to changes in geology, you can interpret lithology from them in terms and fluid content from them, interpret environment of deposition, structural and stratigraphic style can be interpreted and all that, just as we've seen in the former page or in the former slide. So that's basically what your seismic interpretation, the introduction we have for now. Then, what are the objectives when you're doing your seismic interpretation? What are your objectives? One, there are so many objectives, but these are the key objectives. Subsurface structural and stratigraphic mapping. We look at the seismic data just as the first slide shows. You map the structure in the area. What are the fold, the faults, and other geologic structures you can see? Are there diaparic structures like saw diapers and all the rest? Okay, identify and mark stratigraphic units. There are different ways you can see, maybe in the seismic data, there are things like channel fields and all that. There are maybe anticlinal structures that are more mound shapes and all that. Different things. You just map the structure and the stratigraphy. That's one objective. Another is to try to do lithology and fluid determination based on what your seismic species are saying. The different shapes you have in your seismic reflections can link or tell you about different depositional environments and different lithologies associated with different, because when you're doing seismic interpretation in general, your geology comes in. It's no longer a question of just guesswork or whatever. Your geology comes in full. All your geology about a basin, your basin, no knowledge about the basin comes into play. How the sedimentary style, the tectonicism, the structural, and whatever information about the basin comes into play. Fluid determination, by looking at your seismic data, you can infer presence of fluid or not, okay? So we'll come back to that. And that is what we call the hydrocarbon indicators and all that. Now, integration of data, when you integrate your seismic data with other data sets, okay, your well logs, your cores and all that, you build a comprehensive model of the subsurface. So that could be your objective. Then reservoir characterization, you describe the subsurface reservoirs that you may have identified, including its architecture, extent, and the presence of fractures and pores, and potential hydrocarbon accumulations within your identified reservoirs. Then you can then do your volumetrics calculations and the extent, by that you identify the extent of reservoir in terms of reservoir boundaries, calculate reservoir areas. You can now do your volumetrics calculation. This is basically the key objectives of doing seismic interpretation in oil and gas exploration. Okay, if somebody is doing seismic interpretation outside maybe a refraction seismic method, his objectives will be different from yours. But our objectives is focused on oil and gas exploration. Okay, so that is that for objectives. So what are these seismic geometries and fascies that you need to look out for when you are doing interpretation? So this is what we'll talk about. In terms of geometry and fascies, They are what we call simple geometries, okay? You're looking at the reflections to see if they are parallel and continuous, okay? Are they parallel? Are they even? Are they continuous? These are some ways that the seismic reflections may occur. They can also occur to be subparallel in nature, okay? Meaning they are not very straight lines or straight events like the parallel ones, and they can also be divergent, meaning that some places are parallel, some seem to not be so parallel, meaning some reflectors seem to be disappearing into the other and all that. That's for simple geometry of your seismic reflections and events. You can also have a situation where your events are progradational in nature, okay? One thing to know is that immediately you pick up your seismic data, I need to point that out. The first thing you do is to scan through your data, okay? Look through your data, know the data quality, and start looking at the facies and the distribution of events in the seismic data, because these are the things that point you to the geology of the subsurface area, okay? Okay, it points you to the geology, points you to the positional environment and all that. Then in terms of progradational geometries of your seismic data, it could be sigmoid in nature, just as shown on the left panel, where you have a dipping events or something like maybe unlapping events and all that. And then you can have also the oblique geometries, where you have top laps and maybe down laps. And then these ones can be used to indicate a clean sand portion of the bed forms, maybe in your shelf regions and all that. Then we have the shingled, where you have thin interval of top laps and down laps reflectors that are being bounded by continuous or parallel events up and down. So these are some of the geometries that will show you that in your basin or where the data came from, you're having progradational stacking pattern or for your that could indicate presence of maybe reservoirs or tell you environment of deposition and all that. And then we can also have what we call complex geometries, where you have the events are not so continuous or they are not parallel, they are not continuous, okay? They show maybe deformed geometries, having a sliding or slumping
I don't know if it's just me. Please, can you confirm if you can still hear the mentor, please? Okay, he's off the call.
I cannot hear him. I can't hear him, sir.
Oh, okay, okay. I think he has a network issue. Please, let's be patient while we wait for him. Thank you.
Hello, can you guys still hear
Well,
me?
yes, sir, we can hear you, sir.
Okay, so
All right.
are we still together? So, so ideally, knowing these different geometries is very important, and these are basically one of the first things you look out for within your seismic data, and while you look through the data. Apart from this, you also look out for other things like the structural style or structural patterns and all that within your data. So this is a typical example of what your seismic facies and their interpretation could be. Now, on the A part, you have a continuous parallel bedding, okay? Continuous and parallel. And what is the amplitude like? You say the amplitude is high amplitude, okay? Somebody can interpret that. This is already interpreted, okay, that it's the interpreter here is linking it to limestone and marl and all that within a basin where the data came from. But for us, let's assume you're doing interpretation in the Niger Delta. You're not expecting to see limestone and marl in the Niger Delta. So even if you see continuous parallel events within your seismic data, you're not going to be linking them to limestone deposition or marl deposition. You can then infer what's sedimentary, clastic sedimentary depositional style that will give you parallel or subparallel deposition with high amplitudes. Okay, where you also have mound shapes, okay, like the panel B and semi-continuous and discontinuous events. And if you look at it, what's the amplitude like? The amplitudes are high to medium. Okay, the person has also interpreted that to be upper part of the carbonate buildup. So these are the ways you look at your data from top to bottom with respect to the time that different events are occurring and the shapes that they have and their amplitudes. The concocted chaotic for the part C, this person has said they are medium amplitude and he interpreted it to be a core carbonate buildup and all that. And lastly, here is a chaotic, showing the position of gravity, mass flows, and talus. Yeah, when you have a chaotic event in your seismic data, for us in the Niger Delta, where you normally see that is deeper parts of the basin where you have turbidite deposits and all that. If you look at them, turbidite deposits, you also see that they are mostly chaotic in nature. So the shape and the geometry of these events will point you to a possible depositional environment depending on the geology of the basin you're working with. So these are basic things you need to have at the back of your mind before you start imagining fault mapping, which is what I know a lot of you are very conversant with. This is another interpretation. I won't bother going through reading this. When I share the slides, you can go through them and all that. And then this is another one where someone has also tried to do a seismic Fashi interpretation by looking at the different parts of the seismic data and deciding whether the events are continuous, high amplitude and all that, graded and all that. So these are the kind of things you have to know when you're doing seismic interpretation. You have to look at your seismic data beyond just mapping faults, okay? So some of you that have done seismic interpretation, the first thing you start doing is start mapping your fault. When I was an intern, I remember some years back, many years back, when I did my internship in one of the companies, what I was told to be doing was fault mapping. So I just pick the faults on the seismic data and map faults. But there's a lot of things beyond just identifying and mapping faults. And that is where I want us to start our discussion from. And that's what we're doing now. So looking at this stack section here, if I'm to ask you, what do you think is the seismic Fashi distribution here? So this is a small exercise I want you to do. What is the seismic Fashi distribution in this stack section you have here in terms of reflection geometry, amplitude distribution, and look, you do that after the class and on your own. You take them section by section in terms of from the surface to like 1.5 1.5 seconds. What's the event like in terms of geometry, in terms of amplitude? If you go from 1.5 to maybe 2 seconds, there's a change in terms of geometry and amplitude. So what do you think? Can somebody tell me, let's do this first part. What do you think? The first part, what do you think is the event like? Any idea? Am I talking to myself? Hello?
No,
No,
sir.
sir, we are with you, sir.
So good. So the early part of this data from 0 to 1.5 seconds, what's the geometry like? Geometry of the data like an amplitude distribution. Can anybody make any attempt? based on what I've been talking about.
So it's like parallel continuous.
Okay. And what's the amplitude like?
Amplitude. Um, is it,
Say what's on your mind. Just say. Amplitude can be high, low, or medium.
okay.
Okay.
It is high.
Okay. So it's high.
Yeah,
You're correct.
yeah,
You can say it's high to medium because if you look at this
yeah, it's
section,
high to medium.
this side now, the amplitude is low. Is relatively low. You can say low to high or maybe medium. The interpretation is based on you. So
Okay.
there's nothing, what you say might be slightly different from what another person says, but on the average, all of you will be saying about the same thing because that's it. So it's parallel to continuous. Amplitude is high, yes. Medium to high. If you say medium to high, you're not wrong. If you say it's low to high, you're not also wrong because this far left side of the data, this side, you can see that at that 0 to 1.5, this side you're having low amplitude. So the next part, which is these other parts, if you want to interpret it, what would somebody else should make an attempt? I need another attempt. Someone else, not Daniel. A lady.
Emmanuel.
Any other person? Okay. If you don't make attempts now, you gotta make it privately on yourself, on by yourself. So generally, this is what I'm talking about when I'm talking about seismic geometries of fascies. Because when you're doing this, you're looking at what you're doing now is what's called seismic fascia analysis. You're looking at the seismic, you're trying to say this part is distinct from this part, let me say here, A, is distinct from B, based on amplitude. You can see that the second part, the amplitude is low, okay? So that's fasci. Changes within the same seismic stack section, there are changes in amplitude that makes this time range 0 to 5 and 0 to 1.5 and 1.5 to 2 distinct from each other, okay? And that points you to possible geology. It's not possible, just points you to geology. Something is making amplitude to be low and amplitude to be high, okay? If you remember from the basics, acoustic impedance contrast and reflection coefficient. When reflection coefficient is high, amplitude is high. When the reflection coefficient is low, amplitude is low, and so forth, and so on and so forth. So these are the things that is making your data to look different. So if you keep looking at this data section by section, breaking them down, you see that there are differences in terms of amplitude, in terms of event continuity and geometry. If you look at this part of the data, the events are no longer, if you come from 3.5 seconds down, if you look at it, the events are gradually not getting continuous again, and all that and all that. If you look at this part of the data, the events are continuous. On this other part, the events are not continuous. These are the geology. These are the things you look out for. Now, when you have a seismic data, let's assume this is just a 2D seismic data that we are having. So you're looking at only this stack section. If it's now a 3D seismic data, remember your 3D data is a volume. You have multiple inlines and multiple cross lines. Okay, so this you look from inline 1 to inline 2 to, or if it's depending on number of inlines it has. If it has up to 100 inlines or 1,000 inlines, you can use a line spacing. You can say after line 1, you look at line 5, okay, in terms of grading. You space your work because you can't look at all the inlines from beginning to end. It will make, you can do it to you get a more detailed overview, but in interpretation, they normally use maybe 10-10 interval, 10-10 spacing, inline spacing interval. After line 1, you look at line 10, line 20. If they want, you can increase the spacing interval to maybe increase or make the grid tighter by using 5-5 interval. It all depends on you and what your objective is and how complex the geology of the area is. Because if the geology of the place is so complex that the geology is changing at every little interval, then you have to look at a tighter grid and look at your data with a closer grid rather. So this is basically what I want you to do in this exercise after the class. You can do it and send within the week. So I would like to see your different inputs. Take a picture. Let me take a picture of this and then make wow, hold on. Share screen again. So take a picture of this and then do your own Fashi interpretation or analysis of this place, and then send what you have in mind or what your interpretation is like. To do this, it will be more ideal you do it with maybe PowerPoint or maybe picture editor, because you need to write on the data. So now you know how you can do that. So that is that for now. So the next thing we'll look at is what we call seismic polarity and phase. What do you mean by seismic polarity? What do you mean by phase? If you're going to be doing seismic interpretation, you must know seismic polarity and phase. So you don't just jump into interpreting your seismic data without, am I still audible?
Yes, sir, you are.
Okay, so you can't just jump into interpreting the data without knowing the seismic data polarity and the phase of the data. And this polarity and phase is determined during processing. Okay, even though I didn't bring it up during processing, I just left it pending. So what do you mean by polarity? So polarity simply means the relationship between the signs of the seismic reflection and the change in acoustic impedance at a geologic interface. Okay. Polarity also determines whether you have an increase or your decrease in acoustic impedance as represented as a peak or a trough. So from our discussions in the past, we all know what is peak and trough. We all know what is acoustic impedance, reflection coefficients, and all that. So what it means is this. What polarity means is if you have, let me get a pen. Just as we've been talking about, you have two rock units, or just as shown in this cartoon, okay? This one has acoustic impedance 1, okay? This one has its own acoustic impedance, and this one has its own acoustic impedance properties. So at their boundaries, there will be a contrast of which at the boundary of these two rocks, there will be a seismic reflection. We already know these things. Now, if the acoustic impedance below is higher than the acoustic impedance above, it will give us a negative sign, Abi. We all remember these assignments. We've done things on them already. And so there will be a positive reflection, and they will call it a peak, okay? And then if you have at the next boundary, let's say below this hard rock, there's another soft rock, okay? So what will happen? The acoustic impedance at this boundary will be a negative. Remember that our assignment. And so there will be a negative, which will be a trough. Now, if you have a positive, you call it a peak. If you have a negative, you call it a trough. That is what polarity is. So in your seismic data, you have to know what you are calling peak and what you are calling trough. There are two ways or two conventions to that. The Society of Exploration Geophysicists, which is SEG that we all know, I'm sure you all are SEG members, identifies that the peak or a positive reflection that is coming from the boundary like is shown on the cartoon, a positive reflection will be a peak, just as shown in this cartoon here. But another school of thought says that when there is a positive deflection, they will call it a trough. So you know that in your seismic wave, when a wave is traveling, it's traveling like this. Okay, so one side is your peak, and one side is your trough. Now, I'm calling this side peak because another way I want to describe it is because I'm right-handed. Most of us in Nigeria are right-handed. You and I are right-handed. If you have a child today, and that child is a toddler, maybe 2 years old, and you notice that the child is trying to eat with his left hand, what do? You quickly correct the child and tell that child, come on, stop eating with your left hand. Use your right hand. Who told you left hand is not good? Is our mindset. We have conditioned ourselves that the right hand is better than the left hand. And so naturally, we tend towards the right, and it becomes a norm. And I don't know, even nature has now made it a norm for us that everybody is doing everything by the right, from the right side. So your right is your peak, which is positive. Another person can decide that his peak is his left. Are you getting me? So you are neither wrong nor right. My peak, my positive is to the right, my negative is to the left. Somebody else can say my positive is to the left, my negative is to the right. Does that make sense? I want a response here.
Yes, sir.
Yes,
So
sir.
if that makes sense, when you have a positive reflection coefficient, and in Society of Exploration Geophysics SEG, which is the American convention, they say, they take it that when there is a positive reflection, we all know what is positive reflection, that the peak will move to the right, which is shown here. Okay, the peak will be to the right. And when there is a negative reflection, the trough will go to the left, which is also what we have here. But the Europeans, okay, the Europeans' convention of polarity does not see it like that way. They take the peak to be negative, to be our own negative. So the peak to them is on the opposite direction to us. So we have somewhat a mirror image of each other, but it's the same thing. So when you have a positive reflection, you have a peak, and the American convention colors it blue. Okay? But the European Convention of Seismic Data will color the data red and point it to the negative to your left and call it their peak. And then anything pointing to the right becomes their trough. So you have to know that. So in Nigeria, we are using the SEG convention, the American Convention of Polarity. So anytime we have a peak or a positive reflection in our seismic data, meaning acoustic impedance contrast is giving us a positive reflection coefficient, we will have a positive flip, which is a peak. To the right, which our peak moves what? To the right. If you get a seismic data that is not coming from, that is not interpreted with the American convention, the data, let's say a data from the northern the European part of the world, their own data will have their peaks pointing to the left. Do you get the point now? So you have to know this thing. If you don't know it, you're going to make a mistake in your interpretation. You have to know the polarity of the data you're working with. This is very, very, very important. Knowledge of your seismic data polarity is crucial for accurate seismic interpretation, enabling geophysicists to correctly interpret reflection coefficients and geologic features. Remember, what is giving you acoustic impedance contrast is the density and velocity of each rock. And then the basin you are working with, Niger Delta, for instance, what are the rocks here? Sandstones and shales. We don't have carbonate. If you go to another basin, you have carbonate. All of them have different density and velocity properties, giving you the different acoustic impedance and then leading to different acoustic impedance contrast. So you must know your polarity. Also, another cartoon is showing here positive polarity, negative polarity. For the American convention, which is the one here, which is what we use, your positive polarity is your peak, which is colored blue. And your negative, your negative reflection coefficient is your trough, which is colored red. So if you have a seismic data that is processed with American convention, when you have the seismic data, if you're seeing a reflection or event that is colored blue, it means it's a peak. The one colored red is a trough. So you already know behind your mind what causes a peak and a trough. But if the same data is to be processed with an European convention, they will flip it by 180 degrees. You know, when you turn something by 180 degrees, it changes, it becomes a mirror image of itself. So the European convention will see your positive polarity to be opposite in nature. Okay? They will flip it to look positive, meaning they will call it the trough, and then call the negative one the peak. So that is that. I'm trying to emphasize this because you cannot ignore this when you're doing interpretation. If you don't know this, your interpretation, you're likely to make a mistake in terms of who is peak, who is trough. Why is it very important? Accurate interpretation, I've already said that. Understanding polarity ensures the accuracy of your interpretation. So when you see some geologic features, like your direct hydrocarbon indicators, like your bright spot and all that, you know who is a peak and who is a trough and what is causing, and then you can infer what is causing who. Then consistency in different basins. In different regions of the world, everybody has to be consistent. So for us in Nigeria, and I think in Africa as a whole, we are using the American Convention. And so if you're working in Niger Delta, for instance, whether the data is from company A or company B or company C, everybody knows that all our data is in the American Convention. So our peak is blue, our trough is red. So peak is flipping to the right, trough is flipping to the left. Quantitative analysis, when you're doing your quantitative interpretation, like your AVU analysis, it also helps you also reservoir characterization jobs. You also have to know your polarity. If you don't know polarity, wahala dey. How do you determine this polarity? How do you determine the polarity of your data? You determine polarity, one, by looking at the data, looking out for known reflectors on your data sets. Are there known reflectors in the seismic data that can point you to the polarity of the data? Two, your well logs. If you have your well log, you look at the well log. From the well log, you know, in your seismic data, you don't know who is sand, you don't know who is shell. And it is your knowledge of acoustic impedance contrast that leads to positive reflection coefficients, and that tells you when there is a sand overlaying maybe shell that is supposed to give you a positive reflection coefficient, which is a peak, according to the American Convention, okay? Now, how do you know also determine this? From your well log. From your well log, you already know your sand and your shale. If you now do a well log and your seismic to well tie, by generating your synthetic seismograph, your synthetic seismograph will now tell you that your sand, the top of your sand, which is a boundary between a shell, a shelly sand and a sand body, is maybe your peak or your trough, depending on the convention you're working with. Then the lithology markers. What are your lithology markers? Where there is carbonate, where there is gas, shallow gas sands, and all that. How do I explain this in details? Okay. For instance, known reflectors. If you're dealing with a marine seismic data, for instance, if you have a marine seismic data, you know that the acoustic impedance in the water body, the density of water is what? 1. Velocity in water is also low, maybe about 1,000 kilometers per second. Okay? And density is also 1 gram per cm cube or thereabout. So the acoustic impedance in water is usually very low. Okay? Now, by the time the seismic wave gets to the ocean floor, which is this boundary, yeah? This is your ocean floor. What happens? You now encounter sediments. And so the sediments will have its own what? Density and velocity, which will definitely be, the density will be definitely be higher than 1, because density of water is 1. Okay? And since it's even salt water, the density may not be exactly 1. It may be even the 0.9 something, okay? Or thereabout. So velocity of the sand body, the ocean floor sand units, you also determine that. So there will be a strong acoustic impedance contrast between the water body or water column here and the sea floor, the seabed. And so you have a strong reflection coefficient. They are the positive, you have a positive ROC, and the reflection coefficient will be very high. The amplitude will be very high. So by that saying, you will now know that your peak, which is your positive reflection, for instance, you're using the American convention, your peak is colored black, as shown here, and then your trough is colored with maybe red or yellow, depending on the color scheme you're using. So looking at the color, look at this color scale for this seismic data. Your peak here is black, your trough is red. So the black continuous line, which is your ocean floor, has shown you that your peak in this seismic data is black. Any other thing that is colored red is a trough. So this data is using a black, yellow, and red convention display. Okay, so your peak is your black, your trough is your red. So by that, you have already known this. Now, another way you know, I said, is the well log. When you do a synthetic seismograph during your well to seismic time, you know you can decipher your polarity of your data from that. The next one is your known geologic markers. Looking at this second diagram on the screen, let me change this to a blue pen. Looking at the second diagram on the screen, you can see we have a water boundary. This is a water column. Okay, boundary between the water and the subsurface is a peak. You can see the red peak symbol here. Now, salt bodies have high acoustic impedance properties. So surrounding rock units above the salt body will give you, at the boundary between them and the salt body, there will be a positive reflection, because there will be a positive acoustic impedance contrast, okay, which is your ROC. Your reflection coefficients will be positive. Carbonates usually have a high acoustic impedance contrast with siliciclastic rocks like sandstone and shale. So if you have maybe sandstone overlying a carbonate here, at the boundary between the carbonate and the sandstone, so let's say this is a sandstone unit, at the boundary between their two, which is here, there will be a peak. This is what this red line is showing you. And at the boundary under, because you're moving from carbonate to maybe another sandstone unit, there will also be what? A trough. So this is how you know who is peak and trough, by observation, by your lithology markers. These are what we call lithology markers, known lithologies that you know that they will give you either a positive or negative based on when you compare them to the surrounding rocks. If you have a shallow gas sand, it will definitely give you a trough and a peak, and so on and so forth. You have volcanic rocks, intrusion within your basin. What are they going to give you? Peak and trough. If you have a unit that is filled with hydrocarbon, they always give you trough and a peak and all that. And so this is what you need to know about polarity. And this is one of the first things you must know about your seismic data, the polarity of the data. So for us in the Niger Delta, we use the positive the American convention or the Sedge convention, which says that our peak flips to the right, and our peak is usually colored maybe black or blue, depending. Now, if you were to bring that into context in terms of your seismic display, remember this diagram is somewhere in your seismic in processing slides that I shared with you. If you look at this, there are different ways you represent your seismic data. Okay, there are wiggle display, variable wiggle display, variable density display, and a combination of variable density and wiggle display. So if you know the polarity of your data, you now know who is peak and trough. For the wiggle display, you already know that because it's a wiggle, you know what a wiggle is. When it's flipping to the right, for the American convention, it is your peak. And when it's flipping to the left, it is your trough. So if you are to fill it in processing with your software, in process, the softwares, you can tell the software, fill up the positive part with a particular color type and fill up the negative part with a particular color type. Is your choice. Now, seismic displays have different colors. This color here on the right is a blue, red, and white color display. Okay? Somebody can also use another color display like we saw in this presentation, in this other diagram or above, or this stack section, black and red and yellow. So you have to know the color display you're using, who is peak, who is trough. Is my red my peak or my blue my peak? It can differ. Your blue can be a peak, your red can be a peak. It depends on what the color scheme or the color display or palette is doing. So you must know. Ask the question if you don't know and find out who is who. If you're looking at your wiggle trace, it's very easy. You are seeing the ones that are flipping to the right. Those are your peaks. The one flipping to the left are your troughs. You can see them here. Okay? And you can decide to fill the peaks. If you're doing your variable wiggle display, which is the panel B, you know, most time will fill the peak and leave the trough. So you fill the peak with black colorations, okay? Just as shown here, you fill the peaks with the black colorations and leave the trough white to remain white in color. So this is for the variable wiggle and area display. Then you have what you normally see during interpretation on your interpretation software is the variable density display, showing you either blue, black, yellow, black, red, or blue, red, white, whatever color choice they use. You must find out who, no matter the color palette they chose, or that is being displayed, who is peak, who is trough. This is the things you must have to know. And one of the ways to know them is by looking at, if it's a marine data, look at the boundary between the seawater and the seismic section. What is that boundary showing? Is it showing you, because that boundary will definitely be a peak. Okay, that's the boundary between seawater and the ocean floor will definitely be a peak, and it will show you, the color is showing you, if you're using the variable density, it will tell you what the color of your peaks are. And then the other column means your trough. And then you can infer from other lithology, or you go to your well to seismic file or do your synthetic seismograph and know. So these things are things I need to point out. As I said in this place, it is very important to understand what color display of your seismic data represents in terms of seismic polarity. What the color display represents is very, very important. Please, and please, you must know this. So there are different ways and different color displays, okay? For variable density display, look at the panel to the lower left, far left, you can see different displays. You can see that here you have A, B, C, D, and you have different color displays that your seismic data can be. The D part, upper D, white and black display. The lower one, you can see a color riot, yellow, green, blue. So you must know which one of them. So I'm pasting this here so you know that the color display of your seismic data is also dependent on the interpreter. Somebody doing the interpretation can choose the color he wants or he prefers. Okay, most people prefer to use this red and black color or red and blue color display. And for people doing processing, we normally use black and white, like this one here. Okay, for those of us doing processing, we normally use black and white, like this one. We like it because it shows all the features. It's not like you're looking at color, you're looking at the real reflections and all that. But the events or your seismic data can be shown in any color, can see different. I also shown here different color palettes. So you must know who is who, which color is peak and which color is trough. Don't assume that you know them, or because of you are very sure that it must be blue is this thing. When you change your software or you're on a different data, please make sure you identify who is peak, who is trough. before you proceed with your interpretation. I don't know if this is clear enough. Any question? Any question? Am I alone?
No, sir, we are with you.
Okay, so your polarity is very important and what they represent in your seismic data displays. The next thing I want you to know is the seismic phase. This phase, I skipped it during processing, and I need you to know what phase your seismic data will be, okay? So your phase is your time shift and the shape of your wavelets or your seismic wavelets. That's your phase, okay? The seismic phase affects the asymmetry and time shape of your wavelets and indicates when maximum amplitude occurs relative to geologic boundaries. So we know that at the geologic boundary, okay, if we have our reflection at, let's say, this boundary and also at this boundary, sorry, and also at this other boundary, for instance, that if this point we are to have a positive reflection, that our seismic will peak to the right, okay? And this in this boundary, if you are to have a negative reflection coefficient, the seismic data will peak to the left, right? So that is what your phase is. Now, in terms of phasing, you're trying to say, at this boundary that I have my peak or my trough, is my wavelength actually falling on this boundary? Okay? Sometimes your wavelength will fall away from the boundary, just as shown in the lower left panel. So your wavelength can leave this boundary where you have the geology boundary as a red line, and then come under the boundary and present itself. So you must know the phase of the data. Your seismic data can have a zero phase, minimum phase, or maximum or mixed phase, okay? So when the boundary between the rock is where your reflection is falling, just like this part of the data is showing, the right part of the panel is showing. You have a zero phase data, okay, or zero phase normal polarity, as it's called, and then zero phase reverse polarity, meaning that at this geologic rock boundary, your wavelet is symmetrical in terms of the boundary. But a situation where the event or your wavelet is not in line with this geologic boundary, okay? This boundary where I'm marking red. So your seismic wavelet is falling right under this boundary like this, instead of lying in the middle of the boundary or having an asymmetrical shape in the middle of the boundary. This is called the zero phase, and this is called the minimum phase. So it's under, or maybe it's even above like this. Now, you need to know the phase of the data. Normally, during processing, the seismic data is brought to zero phase. All the seismic data is brought to what? A zero phase data. So it means it has to be like this, the one on the right. This one on the left is not how it is. If the processing geophysicists do not bring it to a zero phase, you will have a problem during interpretation of your horizons. Okay? Or you must know the phase they put it. If they use minimum phase, you have to know. If they use zero phase, you have to know. If you are assuming it's zero phase and you go and while it's minimum phase, it means that because the geology boundary is here, if you are to map a horizon, okay, if you are to map the horizon, you will be mapping the horizon to be here, or maybe you'll be mapping it to be here, because this is where the seismic wavelet is falling. So you are mapping your horizon like this, whereas the actual horizon is this place. Okay? So it will give you a wrong interpretation. So you need to know your phase. So it's very, very, very important you know your phase. If you don't, whether the seismic data is zero phase or minimum phase, very important to know. Zero phase seismic data, they are symmetrical, okay, as shown in this diagram, and they fall in the middle of the geologic boundary, okay? So you have the geologic boundary cutting across the peak or the trough of your seismic wavelets, or your reflections wavelets. And so you have a zero phase. But if you have a minimum phase, just as this shown, it is not cutting across at the middle as it should. Okay, so the geologic boundary is actually here. But if you're doing interpretation now, see where you'll be going to think. If you think that is zero phase, whereas it's minimum phase, you'll be mapping this place as a geologic boundary, meaning you have an error, a time shift in your error, and a time shift which is an error in your data. So you need to know these things. My data, is it zero phase or minimum phased? Is it what polarity? Is it the Sedge American Convention or the European Convention? So in the Niger Delta, we are using the American Convention, and here our data is in zero phase data. What do you mean by mixed phase? When you acquire the raw seismic data, some of the seismic wavelets will be zero phase, some will be minimum phase. If you acquire seismic data with vibro size, the data will always have a minimum phase, will be a minimum phase data. So in processing, that's what we call phase correction, where they correct it and bring everybody to a zero phase, so that where you have a peak or a trough, it means it signifies the boundary. The middle of that peak and the trough is actually a geologic boundary. So this is actually very important in your interpretation. You need to know these things. So how do you determine your seismic polarity and phase? So correctly assessing your polarity and phase is crucial. You never you assume that your polarity and your phase, what are they? To know your phase, ask question, or you do what you call, you read your processing, what's it called? Processing reports. I told you about seismic processing report. After the processing job, they give you a report. Read the processing report. Confirm the polarity and phase with interpretative what? Observations. Okay? How do you do this? When you look at I've explained that the known geologic boundaries like the seafloor or known lithologic markers. Do your well to seismic tie analysis. You also determine your polarity and also your phase during your well to seismic tie analysis. Then your direct hydrocarbon indicators. Okay? Your polarity and phase is very important for you to do your DHI analysis. What we call direct hydrocarbon indicators, your bright spot and all the rest. At the end, we'll take a better look at them. So what does interpretation challenge that you can face in terms of polarity and phase? If polarity and phase are not properly identified, it can lead to misinterpretation of subsurface features. Mapping of horizon can be wrong. Amplitude anomalies, which are related to your hydrocarbon indicators, can also be wrong because you interpret them wrongly because you don't know the phase of your data. So that is it for now. Also, in terms of polarity and phase, they can change. There can be a polarity and phase change, okay, which is also a type of hydrocarbon indicator. We also see that. During seismic interpretation, phase and polarity reversal is localized, okay, which is a normal anomaly that you see in some seismic data, and they can point you to the presence of hydrocarbon within the subsurface. Okay, you know that normally you have a zero phase data as shown on the far left here. And this is the way it will appear. Zero phase and polarity is the normal peak for positive, which is the American Convention. Now, if within the same geologic boundary, as you're moving from left to right, along the boundary, if the polarity keeps changing, by the time the polarity has changed, the phase keeps changing, by the time it has changed by 180 degrees, as we have here, what happens? You have a mirror image of the original. The original is at 0. So at 180, you have a mirror image of the original. So your peak now becomes a trough. Your peak becomes a trough. This can happen in the subsurface. And when it happens, it's called what? Polarity reversal. Your polarity has reversed. And what can cause it? Presence of hydrocarbon in the subsurface can cause polarity reversals. We'll see that in some start sections I will show. So when that happens, you have a what? Presence of hydrocarbon can cause that. Velocity and density contrast in the rock can also cause that. So if a polarity and phase change will then occur, which is an indication that there is possible presence of hydrocarbon in the subsurface. So in a situation where you don't know what the polarity and your phase of the data is, you can also start making mistakes in these judgments. And that is why it's very important to know your phase and your polarities and your phase. What is the significance of your polarity, phase change and polarity reversals? They are very important in terms of your direct hydrocarbon indicators, okay? They are useful for your amplitude versus offset analysis. They are also useful in your reservoir characterization, and they are useful for you identifying structures and stratigraphic features within the rock. Okay, so what does this all mean? For your DHI, we'll have slides for DHI. When we get to DHI, I'll explain that. Amplitude variations versus offset. I won't be giving details into that. In what that means, we won't have time to finish that if we start talking about that. What it means is that with increasing offset, your amplitude will change. And when that happens, the amplitude will change, the phase will also change in the data. And so that can tell you whether there is a presence of hydrocarbon or not. And when you're using all these things, your DHI, your AVO, and all the rest, what you're doing technically is your reservoir characterization, identifying a reservoir and characterizing its extent and all that. And then you can also use polarity and change phase reversal, phase change and polarity reversal for structural interpretations and stratigraphic interpretations. So all these are plenty discussions. This is what it means. Let me get a yellow pen. So all these are discussion. This is what it means in terms of polarity and phase reversal. Note, I want you to also have in mind, when you say polarity reversal, it's also a direct hydrocarbon indicator. Okay, it's also a DHI. It's also a way to know your DHI. Look at the stack section on the left, the crop off of this stack section on the left. The part that has been zoomed into, you can see, if in this seismic data now, your peak is a blue, for instance, as you're moving along this boundary, along this event, okay, look at this event here at 1,200 milliseconds, your two-way time. You can see that when they zoomed in, you are seeing that this event is blue in color. All of a sudden, it changes from blue to red. What does it mean? That this yellow pen is not bright. What does it mean? It simply means that the seismic data was seeing a trough all of a sudden. On the same geologic boundary, all of a sudden, a place that used to be, that it was seeing a peak rather, which is positive. All of a sudden, there is a flip, a 180-degree flip of the seismic event, and it turned to a trough. Why? What can cause it? Why would such a thing happen? That in this seismic event, you see this event now that is being zoomed into, is a continuous geologic event. There's no fault here, but all of a sudden, the rock, the property of the rock changed such that acoustic impedance contrast at this boundary was initially a peak. Okay, we're assuming that the blue is the peak. Okay, was initially a peak. Okay, and all of a sudden, it turned to a trough. For instance, it's actually a peak or a trough in the beginning. So what can cause this to happen? If you look at this very well, you also notice there's a kind of flatness around here. So this is pointing you that there's change in the property of the rock around here. What causes those change? Fluid content You remember that we are looking what causes acoustic impedance is density and velocity. And what will make the density of a rock, what controls the density of a rock? If you go back to our initial discussion on seismic method, remember what controls density is what? Mineralogy, pore spaces, fluid content. Remember that slide? So if you remember that, it means that something inside here has changed that made this event that is dipping this way to change its property all of a sudden. So what changed? And whatever changed affected the density and possibly the velocity, because the fluid content of a reservoir of a rock will also determine how fast seismic waves will pass through it. So the density and velocity around here suddenly changed from what it is around here. And so at that point where there is an acoustic impedance contrast, there became a what? A polarity reversal. So you're having blue event, which is, we're assuming it to be a peak. All of a sudden, it turns to what? A trough. Why? Another way I can try to explain that, have we gone 1 hour, please, moderator, so that I know how fast or how
Yes,
slow
we are past 1 hour.
over. Now. Okay. Remember, another way you can talk about that, if you look at all this place now where this structure is zoomed, this event is zoomed from. If you look at it in a bigger scale, you can see this anticlinal structure. Are you seeing this anticlinal structure? What it means, if you're seeing that anticlinal structure, if I'm to draw it out, this anticline, remember in your petroleum geology, what are the petroleum system elements? You have your source rock, you have your reservoir, you have your cap rock, you have your faults, your structure, which is your traps, and then you have your overburden. And you know that for your reserve petroleum to be trapped, we need to have a structure like this, an anticlinal structure, where you have the cap rock. Then under the cap rock, you have a reservoir rock. And then, and so on and so forth, whatever else can be under, something else can be under. Now, if you have an anticlinal structure, inside the anticlinal structure, you are going to have hydrocarbon accumulation. That is, if you have a petroleum system in place, you are going to possibly have a hydrocarbon accumulation. So the cap rock, what's the cap rock? It's usually shale, right? It's usually a shale. I want to break this down. Someone with me? Yeah, I'm hearing you.
I said yes, it's a shale.
Yeah, good. You have your cap rock, usually a shale. And then what will be the next thing? Your sandstone will be under. We are using Niger Delta, for instance, where you have the Abada from Abada, the Akata, and the Benin Formation. So where do we have our reservoirs in the Niger Delta? Which of the formation?
The Agbada Formation.
Good, the Abada Formation. And it's a parallel sequence of sand and shale, for instance, right?
Yes, sir.
Good. So your cap rock is your shale in the Niger Delta, and your reservoirs rock is your what? Is your sandstone. Now, if you to bring in rock physics into this cartoon now I've drawn. In the shale now, you have your density and your velocity, which is acoustic impedance. In your sandstone, you have your density and your velocity. You're expecting that in the shale, the shale and the sandstone, which one have higher acoustic impedance? If we remember,
the shale.
The shale. And so it will have higher acoustic impedance than the sandstone. So the boundary between the shale and let me get a red pen. Okay. So the boundary between the shale and the sandstone, there's going to be a negative event, right?
Yes, sir.
They are going to be a negative. And so if there's another shale under here, then at this point, they are going to be a positive, right? Okay.
Yes.
So here is a trough, and here is a peak. So at this boundary, you are supposed to have a trough because it's a negative. And then you're having, meaning that from this seismic data we're analyzing, that blue, let's assume this blue now is what? A trough. All of a sudden, it changes from trough to peak. which is red, meaning that within this sandstone, you know that in your petroleum system plan or LM, if you have this anticlinal structure, if you have an hydrocarbon accumulation, there will be oil and gas around here. So around here, we have the oil and gas. The property of this sandstone or the reservoir rock will be different from the other part of the reservoir that is containing water. Do you get that point? And so when that happens, immediately the seismic wave gets to this point. Normally, this part where the rock is sand overlying shale that contains ordinary water, it will give you, we have said that it's supposed to give you a trough, right? It's supposed to be a negative, a trough, which maybe they are coloring blue. Now, on getting to this part of this data, or the subsurface, where the seismic, rather the rock unit, which is the same sandstone unit that's giving you trough on this side, because it's filled with brine or salt water. The same sandstone unit, on getting to this seismic wave, getting to the parts that contains hydrocarbon, the density and the velocity of the rock will drop. Okay, the density and velocity property will be affected, okay? And so if that happens, you are going to have a reverse in polarity. Either the velocity and density drops in such a way that instead of having a trough or a trough, your phase, the phase of the seismic wave will change. The polarity will now flip and you now have a peak. That is why at that boundary, at this boundary where you have the same rock unit, but at this boundary, there's a polarity reversal. So it's affecting you, it's affecting the seismic in that way because of the fluid content changes. And okay, so your density and porosity, velocity has changed. That causes a polarity reversal. Another way you use your polarity reversal is for structural interpretation. Look at the panel to the right. We'll try to use it for structural interpretation as shown on the panel to the right. What happens here? You can see what appears to be a fault. Why is it a fault? It's a fault. You are seeing the fault outline as this. It's outlining like this. Okay? Why did you conclusively say there's a fault here? You can conclusively make this inference because if you look at this, the display on this other panel to the right, you're seeing red and black. The peak could be black, yeah, your trough is red. Now, at some point, let's say here that I color blue. This my blue is not very distant. Let me get a sharper color. So this part that I color, I circled red. Look very well. Look at the red. Very directly meeting a black. That's a reverse in polarity. Why? Why is it like that? Because in geology, you know this is a fault. Normally, this is a rock unit. If this rock unit gets faulted and you have a normal fault, for instance, you have something like this. Need somewhere better to draw. Okay, you have 1, 2, 3 rock units. This is sand, this is shale, for instance, and this is maybe another shale. If there is a fault here, it will appear something this way at the end of the day. What happens? This is shale. This is shale. This is sand. This is shale. And because there's a normal fault here, your shale will be here, and your sand will be here, and another shale will be here. What happened in geology, we call it juxtaposition of sand and shale. So your shale sand here is meeting a shale because of the faulting. And what happens? Your polarity around the sand, okay, is supposed to, the boundary between sand and shale, the polarity is supposed to be what? Supposed to be negative, and the boundary between shale and sand, your sand and shale, your polarity is supposed to be positive. Am I correct? So if that happens, it means that at this point, you're having a positive polarity meeting a negative polarity. That is why what you see somewhere, something like, if you look to where you have faults in this data, you now see black meeting white, meeting red. Okay, your black polarity or your black colored event meeting a red one. It's also what you see in areas where there is faulting. Okay, a sudden change in acoustic impedance property. Okay, or a sudden contrast in acoustic impedance properties, where you now have red meeting black, or your polarity, what we also call polarity reversals. What that means is that you are having a juxtaposition of different rock types that have different velocity and density properties. And so if that is continuous and it has a trend, you can now say, yeah, there's a fault here. There's another fault here. There's a fault here, and all that, and all that. So these are the simple things I need you to also have at the back of your mind before we proceed. So this is a typical example where you're showing seafloor reflection, showing strong reflection over the seafloor due to the acoustic impedance contrast between the ocean water and the seafloor bed. And then this other part that is zoomed is showing you polarity reversal within an supposed reservoir rock by maybe due to presence of a hydrocarbon or whatever that may be causing that. Then the next thing we'll talk about today is direct hydrocarbon indicators. So is there any question in terms of polarity and phase? Are there any questions?
Okay, sir. Sir, I have a question.
Okay.
Okay, sir. How do we recognize the phase when we see seismic? Like you were saying something about zero phase, minimum phase. How do you know that, oh, this seismic is zero phase, this is minimum phase?
Okay. How do you know it's zero phase? How do you know it's minimum phase? Good. If you look at this place, this, for instance, where you have, look at the last panel, okay? Where you have a juxtaposition, overlay of a variable density, which is red and black, red and blue, overlain by the wiggle display, variable density display overlain by wiggle display. Are you seeing that?
Yes, sir.
So you can see which one is peak here, which one is trough, using the search American convention. Which color is peak, which one is trough?
Red is peak, while blue is trough, sir.
Good. If red is peak, and you have, for instance, let's use this interval here. Your red is peak, and your trough is blue. Now, where the peak is, look at the seismic wiggle on the red. Is the seismic wiggle balancing on it? Kind of. Is it balanced on it? Meaning,
A bit, sir.
yeah, it's relatively balanced on it. If you look at this small one now, look at this small one. You can see that if you put a straight line in the middle here, you will divide this seismic event into two, meaning it's symmetrical. Does that make sense?
Yes, sir.
So it's zero phased. If it is not zero phased, if you put this wiggle on this symmetry, on this the variable density display, it will not appear in the center of this red line or this red event, because if you put a straight line in the center of this red event, you are dividing the peaks phase, they are symmetrical. So you are dividing it and you're getting a symmetrical division, meaning what you have above is what you have below. So if you're to pick, if you're having this, your horizon mapping, when you're mapping your horizon, you map your peak. For instance, if you identify the peak to be maybe the base of a reservoir, if you're mapping the base of that reservoir, You're mapping it with confidence. Maybe your boundary between your sand and your shale. You map it this way to be confident. You have confidently, you have known that. Another way you determine the phase, whether it's zero phase or minimum phase, you have to look at your processing report. Generally, when you process seismic data in this part of the world, it will be in zero phase. We process our data in zero phase. So if this is a geologic boundary, being overlain, you have a sand shell overlay, for instance. At this boundary where the reflection will occur, you have what? A peak. And it is going to be symmetrical.
Okay.
That is your zero phase. If it is like this, instead of the event to be like this, it will not come and the peak will not come under the geologic boundary and stay. Okay? Or maybe it deviates away. Do you understand? This is the
Yes,
geologic
sir.
boundary, but it's deviating away. If it's like this is minimum phase. This is zero phase. Now, this is another phase. It could be to maybe 45 degrees or 80 degrees, depending on how many degrees. But during processing, the idea is that we make sure that our seismic data is processed such a way that it will be at what? Zero phase, 0 degrees. Okay? So this is minimum phase. Okay. So if minimum phase now, the geologic boundary is here, but your peak is below it. Do you get that point now? Your peak is below it. If you're using a zero phase seismic data and you want to map your horizon, for instance, let's say this one is zero phase, for instance, and you're not putting this wiggle on it. Your boundary between one rock and the other will not be falling in the middle like this as we are taking it. It will not, you will not be assuming that it's going to fall somewhere here. And you know that resolution of seismic data is poor. This small change, this small shift that you have done is looking small to you, but in the subsurface is a big change, is a big difference. It can be up to 10 feet difference. Okay, can be up to 10 feet difference or more than that or less than that. And so, meaning that if you're not saying yeah, my reservoir top is at 8,300 feet subsea, and the drillers are going to drill with this mindset. When they get to 8,300 feet, they will not see the top of your reservoir because the top of the reservoir is there, okay? But your seismic interpretation is interpreting it to be here because your data was zero minimum phase. So they will come here, get to 8,300 feet, they didn't see it, and they keep going until maybe they get to maybe 8,300 and maybe 20 feet. That's when they now saw the top of the reservoir. So this is the reason why, remember one of the reasons why polarity and phase, we have to be consistent. It gives you consistency across a region. All the data processed within a basin has to be consistent with each other because of interpretation. So you don't run into confusions. So that is that. Determining them, one, you look at your display. Two, you look at your well to seismic time. You do a well to seismic time analysis, generate a synthetic seismograph. The synthetic seismograph will show you both your wiggle and your wiggle and your wiggle traces, and then your synthetic trace, and that is variable density displayed, and then you overlap it on your seismic data. When you overlap it, you see how it fares. And then lastly, look at your, what's it called? Your seismic processing report. That is why I try to bring processing into all these things, so it don't sound strange to your ears. You look at your seismic processing report, they must indicate what they did in somewhere in the report. You read through the report and know. Any further question? How many minutes more do we have?
Yes, I have a question, sir.
Yeah, go ahead.
So is it possible that the synthetic seismic that we are overlaying on the actual seismic
Is it possible? Is it possible that a case may come where they don't tally or where they don't
Yes.
match?
Yes. It's not. They will not always match. They will not always match. So why they will not always match is because of resolution difference. Okay, you know your seismic data is measured in time, and remember your seismic data are not going to be seen, and the resolution does not allow it to image smaller geologic features. Okay, so it images larger geologic features, so ranging into tens of feet in thickness. But your seismic data, your well log, is used to log the subsurface and get the true subsurface rock information, and the resolution is in feet, in small units, like 2 feet and above. So your well logs have a better resolution than your seismic. And so when you generate your synthetic seismograph and match it to your well log, they will not match 100%. Okay, there will be a small time, a shift. And so you need to do a bulk shift, what they call bulk shifting, and adjust it. So when we go into that, I will show you that well to seismic type. Yeah, it will not always tally. So there will be a bulk shift to tally it. But the gap between them will not be very significant. They won't be too far from each other. And then you match your strong events together. Does that answer your question? Okay.
Okay, sir. Sir, is it possible that the reflection coefficient shows you that, okay, the reservoir top is on trough, while the synthetic seismogram tells you that it's on peak? Like, are they not supposed to communicate?
Yes, ideally they are supposed to communicate, but in situations where there's a polarity reversal, yes, you don't just use only what you know. Your well is giving you information in one point, so you have to look at an overview. Okay, an overview of what your whole seismic section is saying, in the sense that, for instance, here now, where this diagram is now, see where the polarity reversal is. Let's assume your well is here. You have a well here. You will not see this polarity reversal on the well. They will communicate accurately amongst themselves, because what is here, what the geology here is, they are the same, because your sonic, you know that your synthetic seismograph, you're going to do that with your density and your sonic. And your sonic is a type of seismic data per se, because what it measures is time, to a travel time of your seismic wave within the well bore and into the formation. So they will tally, they will marry, because your well is showing you information at just this point. But the advantage of the seismic data, remember, it gives you information in a large spatial coverage. So your velocity reversal may not fall exactly where your well is. And even if it falls where your well is, what well will be seen is what the information that is at that particular point is. And if it's reversal, your well will show you reversal, your seismic will show you reversal. So they will marry themselves. But when you look at it in a wider view, you now see this reversal from this point, because if you look at this is if you look at this, you will see a flat spot somewhere here. That's what I try to mark here. That is showing you that this is a potential reservoir. So if you look at, before zooming, there's a flat spot here. So meaning this is typically a reservoir. So if you put a well anywhere within around here, your polarity reversal will tally between what is on the well and what is on the seismic around here. But by looking at the seismic stack section which gives a wider coverage, you are not seeing that polarity reversal away from where your wells are. So I don't know if that answers your question. At the well point, yes, they will marry. They will
Yes,
be the
sir.
same, because the velocity your sonic will read will be approximately what the seismic also read. So they will kind of marry themselves.
Okay, sir. Thank you so much, sir.
Good. Thank God. So next, we'll look at some DHIs. And then from next week, we start looking at this workflow for seismic interpretation and how it's done. But why I took time to talk about these things is these are the things you need to know when you start talking about seismic interpretation. So what we basically know as interpretation from school is that, hey, come and map faults. As I told you, when I did my own internship some years back, I was just busy mapping fault. I didn't know what is polarity reversal. I didn't know what is DHI. I just focused on faults because it's very relatable to what we have been talking in structural geology class. Except your school curriculum has been advanced to meet modern day industry trend or business, you may not hear about polarity reversal in the classroom. That is why I try to bring up these concerns or these things to your awareness. But when you talk about map faults, there. What if you are in a basin that does not have faults? Let's say you are in a basin that is not Niger Delta, and you have to map stratigraphic changes. Those stratigraphic changes will be coming in the form of polarity reversals, because it's the change in geology from one rock unit to the other that will cause change in acoustic impedance contrast and change in what? Change in polarity and phase. So stratigraphically, you will not be seeing what we know very common to us, like fault mapping. That is very common. You start seeing things that are not faults, because tomorrow you may be doing interpretation beyond the Niger Delta, which Niger Delta is highly faulted. Agreed. What if you are dealing with a data that is less faulted than the Niger Delta? What happens? How do you identify stuff? Like this one now, this particular slide we are looking at is not highly faulted. Okay. And the place they are showing up polarity reversal, there's no fault there. Okay. This point that they are showing polarity reversal, there's no fault. So if you don't know what polarity reversal is, you will be focusing only on faults, because to look for your traps, which is your one of your petroleum system elements. But your hydrocarbon accumulation can accumulate in any other anticline that is not fault related. So your hydrocarbon reservoir can be non-structurally deformed, could be stratigraphic in nature, and there is no structural confinement to the hydrocarbon. So how do you know? How do you find out their presence or infer their presence? Because for us, what we are conversant with is looking for structure. That's what we are told, or we are more often hear your structures, your structures, your structures are your structures. And the Niger Delta confirms that for us. Outside the Niger Delta, where it is not 100% about fault, how do you know, identify the presence of hydrocarbon? And you can see that from this event, from this other slide we've been talking about, there's no fault, but there is an inference of hydrocarbon occurrence due to polarity reversal. So finally, on this polarity reversal, it is also a type of hydrocarbon indicator. So for your DHI, there are different DHIs. Okay, DHI simply means anomalous seismic responses, just like the one we've seen earlier, that can be used to indicate the presence of hydrocarbon accumulation. Okay, they occur where there are significant pore fluid changes that leads to the elastic property changes of the subsurface rock. In terms of the bulk rock properties, in terms of its density property that is affected by what affect density, the mineralogy, the pore spaces, the fluid content, and all that. So in general, they are called the fluid effect. DHIs display one or more type of characteristics that are consistent with hydrocarbon filling pores in rock matrix. So there are several DHIs. One is the bright spots, polarity reversal, dim spots. There's also flat spots. Now, if you look at the graph to the right, you see with increase in depth in any basin, okay, with increase in depth within any basin, you will see that increase in depth is related to increase in age. So as you're going deeper into a basin, the age increases and the depth or time increases. Now, you will have acoustic impedance response of different materials or basin subsurface rock properties. Like, for instance, shale, the acoustic impedance will be low, and then as you're going deeper, it keeps increasing, and at a point, it seems to be constant with increase in depth. Then water sands that are filled with water or brine, the acoustic impedance tend to increase with increasing depth, and they keep increasing until as depth increases. The same thing happens with hydrocarbon saturated sand. Their acoustic impedance is usually very low. Okay, they are usually very low compared to sand and water. Sorry, sand saturated with water, and also shale. And then it also keeps increasing with increasing depth. So what happens at the shallow part of a basin, where you have mostly unconsolidated sediments? Okay, you have what we call bright spots. You have what? Bright spots. But as your basin increases, the depth of the basin increases, you expect to see things like polarity reversal, and then you also expect to see dim spots. Why? The acoustic impedance property of the different rocks keep changing as depth increases. That's just the summary of it all. So where you have acoustic impedance property of shaly materials or shales higher than that of reservoir rocks, and what will you have? Immediately you have the presence of hydrocarbon, because there is a significant increase in the acoustic impedance property between the cap rock and a reservoir rock that is filled with hydrocarbon, like sandstone filled with hydrocarbon, like you have in the Niger Delta. There will be a bright spot. But a situation where the acoustic impedance for shale drops below that of a water-filled rock, okay, or a water-filled, brine-filled reservoir rock, you have maybe a polarity reversal. And if it also encounters a hydrocarbon-filled reservoir rock, where in a situation their acoustic impedance is becoming quite similar to each other, there will also be a polarity reversal. Then for the dim spot, you have a dim spot where you have at great depth in a basin, where you have acoustic impedance of your shales being much more low, a bit more lower than that of the reservoir rocks. So you have a what? You have a dim spot where the acoustic impedance of shale is lower than the reservoir rocks itself. So you have what? A dim spot. So how do we go further to explain that? For your bright spots, it's normally localized, where you have high amplitude that are associated with hydrocarbon accumulation. Okay, this high amplitude reflection are caused by significant acoustic impedance contrast, just as shown here. There's significant acoustic impedance contrast between the sand body and that's the reservoir rock and the overlying cap rock. So what happens? There will be an acoustic impedance contrast that will give you a high amplitude reflection or event, and that is called a bright spot, as you can see here and also here. So it will give you rise to a bright spot. How many minutes do we have?
We have 4 more minutes left,
Wow.
sir.
And you aren't calling my attention. Okay. So
Sorry about that, sir.
okay. Then another of the DHI is the dim spot. where we know that the acoustic impedance property of the overlying cap rock becomes lower than the reservoir rock. So what happens there? Amplitude around there dims, okay? So having high amplitude reflection coefficient, the reflection coefficient will become reduced. And so there will be a dimming of the amplitude. And so you call it the dim spot. And also around that area, you can also have a polarity reversal, just like this. You can have a polarity reversal. The next one is a flat spot, where you have an amplitude that is relatively flat compared to other events, other amplitudes that are inclined, okay? Where you have this flattening of amplitude is caused due to presence of a contact. That contact is usually maybe between hydrocarbon and water. Hydrocarbon water contact, maybe gas oil contact, or water and oil contact, oil water contact. They can also give you rise to a flat spot. So here, take a picture of this, try to interpret this. Which type of DHI are you seeing before our time finishes? What type of DHI are you seeing? Take a picture of this, share it on the WhatsApp group. I think this is where we end for today. And try to do your own interpretation of simple DHI that you're seeing. Any DHI you can identify on this. Have you done that, moderator?
Yes, sir.
Okay. So the next slide will give the answers, but I won't go to the next slide. I think this is where we call it a day. I want all these things came from the internet. You can, when you read, you come across them. So, and some of my books and all that. So when you study, you come across this all these concepts. They are not hidden, they are general knowledge, and I want you to be conversant with them. So with this, I'll call it a day from here. I want to see your attempts in trying to identify DHIs and also trying to do seismic partial analysis, which is the first assignment I've given. So with this, I'll call it a day here.
All right,
Thank
sir.
you
Thank
so
you
much,
so much, sir.
Thank you, everyone.
Thank you, sir,
Thank
for the
you.
wonderful section, sir.
Okay.
Thank you so much, sir. And we
Okay.
have come to the end of the class. Next class, please, let's come on time. It's very important because that will be the last class for this program. Thank you, everyone, for staying from the beginning to the end of the class. I really appreciate you. And thanks for joining us. See you next week. Do have a pleasant weekend. Thank you.